Hopefully, you all are starting to see this theme, right? Like Bill talked a little bit about data collection. Turns out, in order to do any kind of performance work, I'm sure you all know we have to collect data. And Andre talked about how excruciatingly difficult it was for them to look at data for creating a VM on Azure, all of the different systems that it had to trace through. So our next speaker is Delyan. He's going to talk about something very similar, but on the mobile side. So Delyan leads mobile telemetry efforts at Facebook, and he will talk about the tools and techniques he and his team have built in order to analyze mobile performance issues in the wild. Welcome, Delyan.
Actually, can we have the slides? Sorry. It's currently stuck on. Okay, there we go. Hi, my name is Delyan. I work on mobile performance at Facebook, and today I'd like to share with you where we come from, where we are today, and where we're going in this space. So usually, I don't seem to have a clicker. Sorry. This got lost. Thank you. Usually I have to justify why we talk about performance, but given the backdrop behind me, I'll skip that part of the talk. But suffice to say that when we were starting with performance on Android, we were not in a great place. 2013 was the year where emerging markets were being saturated with fairly cheap devices. That also happened to be where a lot of our growth was. Our product was growing really rapidly as well, as was our company. And so at the end of the day, we were faced with some pretty serious performance problems. It looks like this. Yep, keeps going. 8 seconds to show the splash screen. Just keeps going. I don't know about you, but at this point, like I would have moved out of this app. But it just keeps going. Yep, goes blank for some reason. Still going. Half a minute. "38 seconds to show content I actually can't show you." And 43.2 seconds to actually start up the app. I think we can all agree that at this point, this is not a performance problem. This is a general experience problem. And this is what we were faced with. So we rolled our sleeves and started tackling it. First things first, you can't fix what you can't measure. So we set out to get some measurements out from production. We started in the most obvious place, instrument wall time. Start a timer when the interaction starts, and when the interaction ends, record the difference. From that type of data, we build graphs like this one. We set out to create these graphs where we are tracking our progress on these metrics. So one of the first things we did was we created graphs that look at the latest production release only. And so we started noticing some interesting things. This is an unnamed metric, but there's some interesting patterns in it. For example, when we release the app, what happens initially is that the fastest devices update first. So the metric is actually kind of OK. But then slowly, as the release sort of spreads out through the Android user base, the metric slows down until we hit the next release. So you can probably imagine what the other dips are. Yes, there are the releases. With a lot of metrics and a lot of time, we started gaining a lot of intuition about what our data actually looks like in production versus how we imagine it should look from local tracing. And of course, once you have time data like this, you can group it by any user dimensions and any device dimensions. So in this case, we have the same metric grouped by connection type. And the slowest two lines on top are, as you would expect, GPRS and edge connections. The fastest two on the bottom are actually Wi-Fi. But what this is also telling us is that there's something going on where even if we really optimize latency of the app without changing how much we're actually using the network, the white line is about as fast as we can get. So we started getting this intuition of where we should invest our efforts, where the opportunities were, and really what was the bottleneck for each one of these metrics. So with enough experience, we were getting like pretty good at diving into the data based on these time durations, but we needed to instrument more. And one of the big problems that we faced was that when we were instrumenting metrics, the data wasn't very clean. Initially, a metric would generally look like this. This is a histogram of a just instrumented metric. You have a really fast cached or hot path on the far left. Then you have what is your normal path in the middle. And then you have an even slower path because you're probably writing to disk or you're hitting a different code path entirely. We spent a lot of time, measured probably in years, cleaning up all of our metrics, splitting these into separate cases so that every single one of our metrics looked like this. This is a normal-looking distribution, a little bit fatter on the left side where we want people to be in the fast case, with a really long tail. Once we had metrics that looked like this, we knew that we were always looking at the same thing all the time, and we weren't really that worried that there were more than one code path involved in this number. And of course, with all of this data, we set out and we used local profilers, all the tools available that we could find, to find the lowest hanging fruit on phones, on devices at our desks, and try and isolate these code paths, see what's slowest, fix it, rinse and repeat. Unfortunately, as we were doing all this, one of the things we noticed was that a lot of our wins were being offset by regressions. So we started instrumenting things so we could diagnose the regressions as well. So we took all of these large metrics and we split it into smaller metrics, with the hope that when something regressed, at least we would know which part of the bigger metric regressed. We also instrumented proxy metrics. These were other numbers that were related to our resource usage during this interaction. For example, things like CPU time, major faults, number of allocations, bytes up, bytes down, that sort of thing. And we also noticed that a very large chunk of our regressions were actually caused solely by experiments. So we built custom data pipelines to isolate these experiments before they were rolled out to production at 100%, so we could warn the team and work with them to fix it before the release of the feature. So when we were next faced with a regression like this one, we actually had a little bit more data. So we have this regression that we actually fixed quite quickly within one release. And we also saw that during that exact same time, major faults were also up by about a similar amount of time, by a similar magnitude, while CPU time stayed stable. So this was giving us hints that, hey, this is probably something related with disk access, and we should probably look at our code loading or our cache loading and investigate those areas locally so we could find the issue. This was basically the state of performance at Facebook for mobile apps for a couple of years at least. Unfortunately, we had quite a few major challenges. First and foremost, dealing with multiple metrics is hard. Regardless of what your metrics are, regardless of its performance or not, just the sheer fact that you have to deal with pipelines of related data is difficult. What we also found was that submetrics were not really stable. What would happen is that people would monitor the top-level metric, and the submetrics would go unused for months until they were needed. And when they were needed, we would discover that some refactoring a couple of months ago actually shifted them, and now they all meant completely different things. On the client side, analytics libraries are generally optimized for zero data loss. That means that there's a bunch of overhead involved to ensure that your analytics data makes it to the server. Unfortunately, for our use case, that overhead was really shifting our performance characteristics, and we were really impacting the metrics if we wanted to collect more proxy metrics or if we wanted to collect more submetrics. And lastly, this was all primarily numbers. We were talking about numeric data that was related, but had distinct distributions. But there were entire sets of problems that we couldn't tackle easily. For example, ordering problems. Did things happen ABC or did they happen ACB? And how did that affect the locking? And how did that affect the lock contention and our queuing? And all of these extra characteristics of the interaction that were just hidden from us. And what did those things only happen some percent of the time? And how did that affect the top-line metric as a whole? These were really hard problems to tackle with numeric data, so we wanted something a lot more structured. Over time, we did add parent-child relationships, but that just wasn't enough. So we started thinking about traces. Can we collect performance traces from the production app? So we could isolate these metrics, and we have a very detailed view of what happened within a single run of a metric. We had some pretty strict requirements for this. The first one was we could not afford, The first one was we could not afford to be limited by the client library again. Or we needed something with incredibly high throughput so that we could pipe as much data about this one interaction as we could. We also wanted different levels of detail. We wanted this to be remotely configurable so that when we had a particular type of regression, we could enable different lenses on the interaction, and we could look at different types of telemetry about this interaction. For example, in cases where we suspect that there may be a regression in how we're using memory, we may want to enable more collection about memory usage and stack traces, perhaps, or just allocation counts and allocation sizes. We also wanted to optimize for the specific data that we had. We no longer wanted to deal with just numeric data, and we wanted to have something that understood performance data, things that have threads and timestamps, but also that didn't have to deal with generic key value pairs and move them through pipelines and on device itself. So we really wanted something that dealt with performance data alone. Once we had this library, we set out to build instrumentation. This library took a while to develop, but the instrumentation was actually probably the harder bit of it. The first thing we wanted that we set our minds to, and we really fought really hard to get, is CPU usage stack traces from the apps themselves. This was surprisingly difficult because neither iOS nor Android actually expose APIs for this. We found ways to collect CPU biased stack traces and collect them in a way that is optimized for storage and efficiency at runtime so that we don't have to send full names and class names and method names in every single trace file. We also set out to collect system counters. We look at this as a generalization of the idea of proxy metrics. Instead of having a metric over the course of a trace, we sample this metric over time. And we could see general resource usage patterns during your interaction. Maybe your network bytes actually go up in a spike and then are not spread out. Or maybe there's something going on with the delivery of the data from the network. And lastly, we really wanted to understand our relationship with the virtual machine, the framework, and the OS. These were probably the hardest aspects for us to debug remotely from our previous telemetry data. So we wanted to get as much insight as we could find about these characteristics of the app's execution. For example, things like garbage collection are the classic Java problem. But there's other things, such as how does the framework handle your view drawing? How does the framework handle your allocations? There's a lot of work that happens in an app that it's not under your control, but you have some partial control over it, and we really wanted to get a better view of this. We code this entire library Profilo, and today I'm happy to announce that the Android version of this library is open source on GitHub. Profilo is part of a bigger story. It is only the client-side part of general pipeline for performance telemetry from apps. It has a bunch of instrumentation in different layers that makes its way into a trace file. So far, so good. That gets uploaded to our web servers, where we perform a variety of manipulations on it. The most important type of manipulation is processing it. we use a Python environment where we parse the file into a trace object, and we extract different aspects of this one trace into different tables. For example, we would have a table that solely deals with CPU stack traces. We would have another one that solely deals with VM events. And we would have a third one that probably only deals with system counters. This allows us to zoom in on different aspects of the app and maintain really easy data access and searchability without having to sift through each trace individually. But of course, we also store the actual trace. So at any point in time, we can view the full trace with all of its data in a single trace viewer. We have a custom trace viewer. This is what it generally looks like. And here I'm showing a trace with two processes in it. The first one is the main process, and the second one is the video play process. And we can see that the CPU time for the video play process spikes up early on, and then sort of grows much more slowly over time. So that indicates that there's a lot of work initially and then some steady state later on. And we can see from the raw numbers that there's about 300 milliseconds of CPU time being spent by this one process during this interaction. So we have 300 milliseconds told to us by the system counters, and we can see that there's about 300 milliseconds actually shown by the stack traces themselves. We can expand these stack traces. We have grouped them by thread priority, and we can zoom in on where different thread priorities are using up this CPU time. A lot of the early work is on the main thread. A lot of the steady state is on the default thread. And then there's some low priority threads that do a minimal amount of work. We can, of course, zoom in into the thread groups. And we can zoom in into every single thread as well and look at the stack traces and where they're actually spending CPU time. In this case, we have some HTTP thread using 51 milliseconds of CPU time right before we enter the steady state. Within the same trace, we can also look at different aspects of the interaction. Here, I've plotted the global allocation count, meaning the number of Java allocations in the virtual machine as a function of time. And we can see that it's pretty linear. We grow from about 0 to about 200,000. But there are areas where the rate of allocation increases, like that area right there. So we may be looking at this trace and be thinking, OK, we're putting more pressure on the virtual machine and allocator. Did the virtual machine respond in any way? Did we cause it to maybe perform a garbage collection? We could start making these hypotheses about what the things we're doing are making the virtual machine do and check them, whether they actually come true. And so we can then zoom in and find the heap task daemon thread, which is the Android garbage collection thread. And we can indeed see that when we put more pressure on the garbage collector, it almost immediately started a garbage collection. And that took about 200 milliseconds. Now, this is not exactly causality, but with enough traces and enough digging through this type of telemetry, we're able to get a very good intuition of how different interactions affect the virtual machine, different OS versions, and how we can optimize our usage of the system as it reacts to us. Unfortunately, when we're dealing with regressions, we really don't want to be spending time sifting through a mountain of traces and trying to find these nuggets of data. So where Profiler really shines is in aggregate trace analysis. Aggregate trace analysis has allowed us to turn regression detection that took us weeks, months at the time, and often left unsolved, into something that could be automated and take days to minutes. I'd like to show you a demo of one of our internal tools now of what the typical process of a new release and dealing with performance regressions in a new release looks like. This tool is called Comparison View, and we are looking at two versions of Facebook for Android that were released a while ago. We're going to start on the left side here. This is Facebook for Android cold start, meaning a brand new start of the app. We can first get a better idea of whether the new version is good or not, whether it has regressed in any meaningful way, by looking at the overview. What the overview is telling us is that the average trace duration measured by two separate independent systems has actually increased. It's increased anywhere between 600 milliseconds or around 400 milliseconds here to 100 milliseconds down here. And we can immediately see other things as well. Average CPU time appears to be up, as do major faults. Class load counts appear to be the same. Therefore, we're going to ignore code loading problems for now. And we're going to try and zoom in on the CPU time. As I mentioned, Profiler has CPU biased stack traces, meaning they're only collected when the CPU clock moves. So we are able to investigate them in aggregate. What we have on the right side is a graphical representation of every single stack trace we have for these two versions of the app. What is happening here is that every node in this graph is a unique frame in a stack trace, while every edge in the graph is a caller-callee relationship. Things that are red are things that got slower. Things that are blue are things that got faster. Things in gray didn't really change on average. And we can see that there's a lot of pink, there's some bright red, and there's some bright blue. So let's try and go at this in a very color-oriented way. Let's go for the brightest colors and just see what happens. OK, so right here in the middle, we have an improvement of about 400 milliseconds and a regression of about another 400 milliseconds. If you look at the class names, what you'll notice is that these are actually the same class that was just renamed, and it was moved into a different package. And because this is something that happens a lot, the tool actually can deal with it fairly easily. We just drag and drop this on top of each other, and the regression cancels out. So that's probably not what we're looking for. Down here, we see a very similar pattern. There appear to be two improvements, these two guys, and two regressions, these two guys. And we can see that this is 1 second and 58 milliseconds inclusive time regression, and this is a second improvement. And then this is 900 milliseconds regression and 850 millisecond improvement. So we can just drag and drop these. The names are weird because this is auto-generated code, so no human actually wrote these class names. We don't actually write code like this. But we see that the functions actually remain somewhat pink. So whatever we're dealing with here, there is some type of regression that involves these functions, but it's not quite as clean-cut as just a rename. OK, so that only leaves us one section of bright red, and that's the section over here. One thing I didn't mention is that everything that has a black bar on it is a top frame in a stack trace, meaning that is the first frame in our own code base. So it's not necessarily the first frame in the stack trace itself, but it's the first one we can do anything about. And so we see that this one has the little black bar, so it's in our code base, and it's the first frame. And we're just going to focus on it for now. Meaning we're going to hide everything that's not transitively related to this one function. This cleans up the graph a little bit, makes it easier to spot changes. And we see that there's this chunk of 5 things happening here. OK. So on top, we have 260 milliseconds inclusive time regression, 300 milliseconds inclusive time regression, 300 milliseconds again, 270, and 320. What's interesting about this is that we didn't see an exclusive time regression except this last one of 7 milliseconds. What that suggests is that the change is not actually somewhere within these 5 functions. It is in who they're calling. So perhaps maybe they're calling their children a lot more often. Maybe there's something else going on, but the time is not actually being spent in those 5 functions. They just show the change in inclusive time. So at this point in time, we have 5 candidates for regression. So we could open up Mercurial, and we can go to the code, and we can open up the blame, and we can try and figure out for each one of these files which one was the culprit. We could also do something else. We could select files changed. Comparison view integrates with a source control, so we can pull up all the files, all the frames that were in files that were modified in the new version. So we can find that, hey, 3 of our 5 were actually in changed files. So that narrows down the potential for where the problem is. But we actually can do a lot better than that. What we can also say is just functions changed. It takes that same version control data and analyzes where the functions are. And it tells you, hey, this function actually has new commits affecting it in the new version that were in the last version. And so with that information, we can open up this one frame. We can look at the details. We can find the commit that affects this this function. We can reach out to the author, and we can debug this regression, which would have normally taken about a week, in what is effectively a 5-minute session with a UI tool. Can we switch? Okay. These are some of our internal tools. So we're not actually releasing releasing them with the open source release of Profiler, but we hope to work with you and the community as a whole to try and identify what would be most useful and where we should spend more effort releasing methodologies like this one. Profiler is available on GitHub. You can go check it out right now. And my name is Delyan, and I think we have a few minutes for Q&A. Right, so there's a mic over there, and there's a mic being pulled out over there. Yes.
So are you releasing the UI tool as well?
We're not releasing the UI tools, but we're definitely very interested to hear what people find most useful. It's kind of challenging to release everything at once. So we want some guidance, and we want to talk to you guys and see what would be most useful and where we could collaborate.
Cool, thanks.
Do you have an iOS equivalent tool?
iOS library is unfortunately not in the same state as the Android library. We are working on open sourcing it, but it's not quite there yet.
Thank you.
Do you see the data you collected in simulated network conditions versus the real?
So the question is, do we see the data being collected being different from the simulated network conditions in the lab? Yes, absolutely. In our case, one of the major challenges is that there's a lot of server-driven configuration, both around experimentation, but also just configuration as a whole. And it is nearly impossible to iterate all the possible code paths locally in the environment, in the lab environment. And the other aspect of this is that the lab environment by design targets the common case, right? We want to detect regressions for the most common user experience. But there's a lot of work to be done for outliers, and those are by definition really difficult to reproduce. So definitely the data looks very different. We try to match them, but they're not quite there. We do use Profiler in the lab as well, which has been a very interesting experience. We use the exact same comparison view and the exact same tools that you just saw to analyze individual lab experiments, so individual A/B runs in the lab. And this has been very useful for the product engineers because they really only have to learn one tool.
When you're profiling about regressions, what is your basis saying? How you know that something is how you compare it?
The question is, what is the basis for a comparison between when we're looking for regressions? We generally tend to look for regressions release over release. So we would look at the previous version, we would look at what the wall time durations were, and then we would look at the current version, what the wall time durations are, and we would compare them at similar points in the release cycle.
It's
do anything? Yeah. I'm curious how you're getting information on events like GC and class loading. Like my understanding is that some of those are native events. Where are you getting the hooks of these?
A lot of these native events. We're getting this by basically enabling what is locally called systrace. We enable that in production, and we capture the virtual machines and the frameworks as a whole right into systrace. We capture those in production. We add the timestamp, add the thread ID, and we put them in a trace file.
Wait. You have native events, systrace for native events?
Yes. So everything you see is everything from the framework and the virtual machine on Android actually comes from our own process, but comes through the normal systrace layer. It is only stuff from our own process because of sandboxing, but it is everything that the virtual machine would give you in local tracing.
That was similar to my question, is how you got some of these stack traces where the OS didn't necessarily give it to you.
It's a really complicated question. I could answer with code better than I could with words. The answer is we have a custom unwinder. We poke at the VM infrastructure manually. We find the data structures, and we unwind them ourselves. That is the short answer. The long answer is that it's more complicated than that.
Thanks.
All right.
All right.
If there's no other questions, thank you for your
Thank you,
time.
Delyan.